recording. Okay, so let's start with our first speaker of the morning, Cambyse Rouzé, who's going to talk about the entropic convergence of Gibbs samplers.
Thanks a lot, David, for the introduction. So this talk is based on the two following papers, which you can find on the archive and at these numbers. And this is joint work with Yvan Bardet, Ángela Capel, and Daniel Stilck França. So the main theme behind this work is that of the interplay between equilibrium and out of equilibrium properties of lattice spin systems. So quantum spin systems at equilibrium are usually described by a Gibbs state, sigma, at some inverse temperature beta, and they correspond to some local Hamiltonians. So this is just a sum of terms that are locally supported on your lattice. And the main question of interest here is how fast do the correlations between two apart regions of the lattice decay in the distance that separate them when the correlations are measured in that particular Gibbs state. And so depending on the temperature, you will either decay very fast or very slowly. And so there exists a critical temperature where the phase transition occurs. However, there is also a dynamical formulation of lattice spin systems. And typically here we are given a Markovian evolution that is generated by this Lindbladian L lambda. And the question that we ask is how fast does this evolution converges to the equilibrium state of the model? So it turns out that classically, properties of the Gibbs state and properties of the Lindbladian influence each other. And the very rough idea is that if thermalization occurs fast, then far apart regions of the lattice will not have had time to correlate by the time the Gibbs state is reached, which basically will imply fast decay of correlations in sigma. And the converse, namely that decay of correlations would imply fast thermalization, is also slightly harder to prove usually, but it's also known to hold classically. So the main question I want to ask in this talk is exactly whether this equivalence still holds for quantum spin systems, and we will mainly and only consider the direction from equilibrium to out of equilibrium here. Okay. So the classical picture looks roughly as follows. Assume that you have a very strong exponential decay of correlations or clustering of correlations in your Gibbs state. Then this clustering of correlations implies a strong notion of entropic convergence of your Glauber dynamics, so your Lindbladian evolution towards the equilibrium state. And that entropic convergence itself implies the notion of rapid mixing. So rapid mixing is basically the fact that variation, the time it takes for the evolution to converge scales typically polylogarithmically in the number of sites in your lattice. So rapid mixing itself is stronger than the non-closure of the gap for your Lindbladian, which itself would imply that you mix typically in times that scale polynomially in the size of the lattice. But what is surprising is that this seemingly weaker type of convergence, this non-closure of the gap itself is strong enough to imply the clustering of correlations that you would need to prove this faster convergence. So in some sense, static phase transition is accompanied by a dynamical phase transition, where at the same time, at the same critical temperature, the dynamics will go from converging very fast to converging very slowly. Okay. So the situation is much less understood in the quantum case. So what we know is an equivalence between the non-closure of the gap and a stronger notion of clustering of correlations, which was introduced by Castoriano and Brandao a few years ago, and this works for commuting Hamiltonians. We also can prove by hand the rapid mixing property for some examples. So for tensor products of depolarizing semigroups, for instance, or for semigroups that converge to something that is close to a graph state, or semigroups that converge to the Gibbs states corresponding to a stabilizer Hamiltonian at high enough temperature. But so far, there is no clear proof of an equivalence between the notion of rapid mixing and the notion of a spatial gap. And one reason behind this is that we don't have a good way to go from some notion of clustering of correlations to entropic convergence. And that's precisely the arrow that I'm considering in this talk here. Okay, so let me emphasize maybe one last time the importance of entropic convergence. So the first reason I already mentioned several times, it will provide a very neat proof to proving this equivalence between dynamical and static phase transition in some sense. The second reason why this is an interesting thing to have is maybe slightly more practical. It would actually imply So if you had entropic convergence, you would be able to get sharp bounds on how well you can distinguish between two Gibbs states in the regime of finite lattice size, and when one of the Gibbs states is the equilibrium state of the evolution that you're considering. So this was proved by me and some co-authors a few years ago. And, and more recently, it was proven that this notion of strong entropic convergence was proven useful in getting bounds on the depth of a noisy quantum optimization circuit beyond which the computation can be classically simulated. And there will be a talk about it by Daniel on Friday. Okay, so here is finally our main result. So we proved that given the Gibbs state sigma of a local commuting Hamiltonian H, there will exist a local quantum Markov semigroup that converges to this state exponentially fast in relative entropy distance if any of these three properties is satisfied. So the first one is that the Gibbs state itself is classical and you're above some critical temperature. The second constitution is when the Hamiltonian corresponding to your Gibbs state is a nearest neighbor Hamiltonian for any dimensional lattice. And again, you're above some critical temperature. And the last case is that lambda itself is a spin chain, so 1D lattice. So what I mean by exponentially fast decaying relative entropy is precisely that this inequality holds. So where for any input state rho, the evolved state rho t is such that the relative entropy distance of rho t from its the infinite time limit, so the Gibbs state, is contracting with a rate of contraction alpha that has to be not depending on the size of the lattice. So I remind you of the definition of the relative entropy between two states. So this is just trace of rho times log rho minus log sigma. And perhaps notice that even in the first situation where sigma is classical, that does not actually mean that you can directly restrict yourself to the classical setting, simply because it might be that you have the entanglement in your initial state might potentially slow down the evolution. So what we prove is that this will not be the case here. Okay. So let me now introduce the objects that I'm considering in slightly more details. So we have a semigroup of quantum channels that is generated by some generator L lambda, some Lindbladian. And more generally, I will consider restrictions of the evolution to some subregions of the lattice, and I will denote the corresponding Lindbladian by LC, which is a sum of local terms. So these LJs are Lindbladians that act only on the site J and its neighborhood. And I will assume that all these local terms have sigma as a fixed point. So sigma is in the kernel of these generators. Now, under some technical assumptions, I will not spend too much time discussing here. We know that there exists for each of these subregions a projection onto the fixed points corresponding to that region that I will denote by EC, and I will sometimes also call it a conditional expectation, such that the evolution converges to that conditional expectation. So if you take C to be the whole lattice, then you basically project onto the only fixed point of your evolution, which is the Gibbs state. So what we want to prove is this inequality once again. So especially for C equals to lambda, but we can also ask the question whether we can prove it for any subregion of the lattice. And so proving this sort of strong data processing inequality is usually difficult simply because we don't necessarily have a good expression for this exponential of the generator. But as it turns out, and it's usually when you consider Markovian evolution, it's usually easier to consider the derivative of the inequality with respect to time. And it turns out that in this situation, again, the derivative will be equivalent to the inequality itself. And its derivative at time t equals 0 is called the modified logarithmic Sobolev inequality. So this inequality has, of course, two sides. From the first side, on the left-hand side, you have this rate alpha, which we want to prove to be independent of the system size. Then we have the relative entropy distance to the fixed points corresponding to the region that you are looking at. And on the right-hand side, you have the so-called entropy production corresponding to that region, which is minus the derivative with respect to time of the relative entropy distance to your projection onto this region when you take the derivative along the evolution. And it has this nice expression. So since we assume that was the fixed point of all these LJs, it's relatively easy to convince oneself that the entropy production will be linear in taking the sum of Lindbladians interacting on different regions of the lattice. So this basically, I'm saying that this identity holds for the entropy production. And that actually suggests that one could potentially decompose the analysis into controlling this constant alpha on regions of fixed size. So that's how we will do, how the proof will go. But of course, for this, we also need to find a good way to control the left-hand side here. So we want to upper bound this relative entropy in terms of a sum of relative entropy distances to projections onto local regions. And that's where all the proof will go. So just for sake of notations, alpha of L will be called the MLSI constant, MLSI for modified logarithmic Sobolev inequality. And this is the best constant that achieves this inequality for all state rho. Okay. So let us, before going to the quantum interacting setting, let us look at what we know about the non-interacting classical case. So this MLSI constant satisfies something that we heard about with the talk of Salman on Sunday, this tensorization property. So it basically says that if you take a tensor product of two semigroups, then the constant of that tensor product is equal exactly to the minimum of the constants corresponding to each of the semigroups taken separately. So however, this property is known not to hold for quantum systems, and by now we have counterexamples to this. And that is exactly the reason why Gao, Junger, and Laracuente considered an extension of this constant, which they called the complete MLSI constant, which is simply defined as the infimum over all natural number, the MLSI constant corresponding to your semigroup tensored with the identity map on an arbitrary large reference system. So it turns out that this complete MLSI constant will satisfy the tensorization property. And I will explain, sorry, I will explain just in a slide why this is the case. However, it's not so clear now whether this constant actually makes sense even when L is acting on a finite matrix algebra, because you're taking a semigroup actually that acts on an infinite dimensional system potentially by taking its infimum. But by now we have actually two proofs of this fact. So we know that the complete MLSI constant is going to be positive as long as L is acting on finite lattice regions. Okay, so let me explain to you how this tensorization of the MLSI constant, or the CMLSI constant works, and in the simplest case of a tensor product of depolarizing semigroups. So let's consider a tripartite system, rho A, B, C, and I will put the depolarizing semigroup on the subsystems A and B, so here only on A. And of course, this depolarizing semigroup converges to the partial trace on the corresponding subregion. And it turns out that the left-hand side of the MLSI, so this relative entropy distance to the projection onto AB, the partial trace onto AB, can be controlled in terms of the sum of two relative entropy distances to the projection onto B and to the partial trace onto A, which is precisely what we want to have to prove this tensorization. And this inequality is simply a reformulation of the strong subjectivity of the entropy. So it turns out that this inequality also holds more generally when you consider other kinds of conditional expectations instead of the partial trace. So remember that for me, these projections are just the infinite time limit of my evolution when we restrict to some subregions of the lattice. And if you take two such subregions, which might overlap, but such that the conditional expectations are commuting with each other, then we get this extension of the strong subadditivity, which is due to Betz. And this again allows us to restrict the proof to restrict the proof to small region of the lattice. However, this commutation relation is a very strong property, and it even for classical systems, it will typically hold only at infinite temperature. So, of course, what we want to prove is something at finite, maybe high, but still finite temperature. And this was achieved in a classical case by Ceci in 2000. And he realized that the clustering of correlations in the Gibbs state is a good property to find the relaxation of this tensorization of the relative entropy, where you have to just multiply this right-hand side by some constant C, which is very close to 1. It's going to be 1 plus some exponentially decay function in the overlap between A and B. Of course, if this constant C is devise an iteration procedure in order to control big regions onto smaller ones, and finally prove that this alpha 1 constant is positive. In the quantum case, so we have an extension of this approximate tensorization. However, for quantum states, we couldn't get rid of an additive constant Q, which is can be written in terms of entropic quantities, that basically encodes the information about the entanglement of your state rho between the region AB and the outside world, and the coherences that might occur at the boundary. And because of this, this argument of Ceci cannot go through directly. So the whole point now is to find a way to restrict ourselves to states for which this constant Q disappears. And then the argument of Ceci would follow. Okay, so the intuition behind this fact is that the time it takes for your system to lose all its coherences and the time it takes to lose all its entanglement should be much smaller than the time it takes for thermalizing. And to make this intuition into mathematical rigor, we will consider the simplest possible case in this talk. So I will take a classical Gibbs state and a classical Glauber dynamics that I will embed into my quantum system. And I will even consider the case of just a classical Hamiltonian that is a 1D nearest neighbor Hamiltonian. Now, if I take a subregion A that I write, so which is this region in red, which is just the union of fixed size intervals, which are separated by just boundary terms in blue here. A corresponding action onto this region A can be also, you basically project onto a critical spin value on the blue regions. And then depending on the value of the spin on the blue region, you just replace your quantum state on the right region by the corresponding conditional Gibbs state corresponding to condition on the value of the spin on the blue region. So just to say that this is basically a classical state, because this is just diagonal in the computational basis, and this I assume was also a classical state. So the hope is that now we can restrict our proof to just looking at these states. And to do this, we will use the chain rule for the relative entropy, which basically tells you that the bigger the region onto which you're projecting, the bigger this relative entropy distance, and you can actually control by how much bigger it is. And so you have this basically triangle identity that holds. So I just rewrote the chain rule here. And now I will control each of these terms separately. So the first term I can control using the tensorization for the complete MLSI. So I can control it by the entropy production on the region A. And the reason I can do this is because remember this union of intervals A is a union of non-overlapping intervals. So they will not interact with each other. And so the whole point of the proof is to find another way, a way to bound this other quantity here. And to do this, we introduce this notion of a pinched MLSI. So it looks very much like the usual MLSI. But on the left-hand side, instead of having the state rho itself, you have its projection onto this region A, this union of intervals. So I will not explain how I get well defined, but we will get back to it. I'm just going to use it for C equals to lambda, directly the relative entropy on the left-hand side. And so I can control now this relative entropy by the entropy production onto the region lambda. And now I just use the production in order to regroup these two terms, so on LA and on L lambda. And this will be my candidate for lower bounds on the MLSI constant. So I already argued that this is going to not depend on the system size. So the only thing I need to argue is that the gamma lambda itself does not depend on the size of your lattice. Okay, so to do this, that leads me to discuss a bit further in details the notion of exponential decay of correlations. So what this inequality really is doesn't matter too much. It's what it means that is more important. So remember that in infinite temperature, we know that any conditional expectations, any two conditional expectations of two different regions will commute with each other. And so what this inequality tells you is even at finite temperature, at high enough temperature, but finite, you're violating this commuting. And by how much is basically given by this exponentially decay function in the overlap between C and D, which I already mentioned before. And that's precisely the inequality that Ceci used to find his approximate tensorization of the relative entropy. And again, we have this constant 1 plus this exponential decaying function as a multiplicative factor in this inequality. So now remember that the state rho A, so this projection of rho onto this region A was classical, so we can directly use Ceci's inequality. And if you do it in an iterative manner, you can easily convince yourself that you can control this relative entropy by a sum of relative entropy distances to fixed size regions, which I denote by Cj here. And K is just a constant that doesn't depend on the system size. Okay, so I rewrote the inequality here. And now we'll just control each of these relative entropies separately by entropy productions onto the corresponding regions. I can do this using my pinched MLSI for each of the region CJs. And gamma C here is just a uniform bound on all those gamma CJs. Okay. Now, the way these region CJs are defined is that consecutive, so their union is the whole chain, and consecutive region CJs only will overlap with each other. So in the worst case, you might be counting one side twice in this sum of entropy productions. And this is the reason why there's this factor 2 that comes up. But that's a price that we're happy to pay. This is still a finite constant. And so at this price, we can just bound this sum of entropy productions by the entropy production to the whole lattice. And the last sort of technical detail of the proof is to find a way now to bound this gamma C in terms of something that is positive and for fixed size C. And the thing that is positive that we will use is the complete MLSI constant itself. And so this is what is in this box here. And the idea is to be slightly more careful in how we choose these regions CJs now. So the way to choose them, and a generic region C of that form will be a region that starts just after a boundary term in blue in the figure below, and will stop just before another boundary term. So I hope that the figure is kind of speaking for itself. So using this sort of decomposition, this geometric decomposition, you can convince yourself that projecting first onto the red dots, so this region A, and then only projecting onto the blue rectangle is the same as doing things the other way around. So in other words, these conditional expectations will commute with each other. And we will use this relation here. So for the last time, let's start with the left-hand side of the pinched MLSI for a given region C. Then I use this commutation relation to flip EA and EC here. Then I can use data processing to get rid of this quantum channel, the quantum channel EA. And finally, I can control this relative entropy distance to the region C in terms of the entropy production corresponding to the same region using the CMLSI. And that's basically the end of the proof in this simple classical setting. So to conclude, so we have the first proof of the existence of these MLSI constants for quantum lattice systems. In the case of so classical Gibbs states, but as I didn't explain it here, but we can extend it to nearest neighbor commuting Hamiltonians and 1D commuting Hamiltonians. And the proof basically uses two main tools. So the first one is a generalization of the strong subadditivity. So this is our approximate tensor of the relative entropy, where we have on the right-hand side in the quantum case, we have this sort of quantum term that disappears for classical states. And in order to restrict ourselves to states that do not have this constant Q, so that this iterative procedure works, we have to introduce this notion of a pinched MLSI, which is this modification of the MLSIs that makes the trick. And an obvious open problem is whether we can extend our results to k-local commuting Hamiltonians. And so I didn't explain why we have to restrict ourselves to nearest neighbor, but there is a reason behind this. And so I think this proof would probably not go through the k-local case, but we have good reasons to believe that under some mild conditions, we should be able with other proofs to also consider these cases. And there will be soon a paper on the archive about this. Okay, so thank you very much for your attention, and I would be happy to take any questions from here.
Thank you. Thanks a lot, Cambyse, for the very nice talk. Okay, I think there are no questions on the Slack so far, but I mean, now maybe some questions are coming. So let me ask first myself. I have some questions, I think. So the first one is related to what you just said about the nearest neighbor. Of course, in 2D or higher, if you restrict to nearest neighbor, probably you are forbidding to have some topological order. So maybe there is some obstruction coming from topological order, which somehow makes sense because this system should be more robust. I don't know if you can comment something on that.
Yes, of course. Actually, so that's a very good question. So basically the reason why, so if you remember the way I studied my theorem, I said there exists a Lindbladian for which things work. I didn't say that you can do it for Davis generators, for instance. And so actually I have a backup slide for this. So we are using actually a construction by Bravi and Viali, who consider this, in the case of the local Hamiltonian problem, where in the case of nearest neighbor interactions, you can simply write your Gibbs state as a product of matrices acting only on two regions. And then you can construct basically local algebras which will commute with each other. And if you do it this way, basically using this Schmidt decomposition, you can construct your local algebras by just basically taking the algebras generated by these local terms. And in some sense, when you do it this way, if you now consider the conditional expectation onto one region, the boundary will look like very classical. It will be like a direct sum of tensor products of boundary terms. And so in some sense, the classical proof follows the same way. Of course, you have to be careful how you define clustering of correlations, etc. But that's the reason why with this kind of generator, so this sum of conditional expectations corresponding to this decomposition minus identity, things work. So it's exactly related to topological order. So here, in absence of topological order, things work fine. And it seems like if you want to go beyond this, it's going to be harder. Yeah.
Oh, very nice. So okay, this also, maybe you already answered, but I mean, for which type of generators can you prove the results? I mean, you have several kind of possibilities, 1D, classical, etc. So, just said, I mean, any type of generators, Davis.
No. So exactly for the nearest neighbor, we have to consider these generators. So whether these conditional expectations are defined through this decomposition of your Gibbs state. So these are not Davis, and we expect that the generator here converges faster than Davis actually, because these basically project onto smaller algebras and the conditional expectations for the Davis maps. So it might be that the Davis itself actually, even for nearest neighbor, might not have this property of fast convergence. This is not clear yet.
Okay, so some questions are coming now via Slack. So Alvaro Alhambra is asking the following: from these bounds, can you prove something like an area law for the steady states of the dynamics?
I guess yes, right? Because this implies rapid mixing, and there are these papers which prove area laws with logarithmic correction terms, I guess, for the Gibbs state, for the fixed point, yes. So I guess you could, yes, from here.
And another question from Frederick Rau-Clausen is, can you use the quantum classical mapping to get new results on mixing of classical Markov chains?
I think not, right? I mean, this is an extension of the classical results in the sense that the dynamics itself is classical. So it's, I think it only says something about the quantum system itself. This mapping would not say much about classical dynamics itself, no. I don't think so.
Okay, thank you very much. So I think Cambyse will be available for in the roundtable after the session. If you have more questions or want to discuss further things with him, thank you very much. So
thank you.